Welcome everyone to another Seds Online webinar. We're really pleased to introduce Mike Clare, Dr. Michael Clare, as our next speaker for the scientific webinar series. And we're also very pleased to be able to offer all of our events for free, thanks to sponsorship from the International Association of Sedimentologists, the IAS. So just to introduce Mike, Dr. Michael Clare completed a master's degree in geology in 2004 before going to work as a geotechnical engineer, initially for a small contractor before moving to international consultancy at Fugro Geoconsulting. He proceeded to work for the next decade as a consultant in oil and gas, infrastructure and renewables. In 2012, he took up a part-time PhD in ocean and earth science at the National Oceanography Centre, alongside his industry role that he completed in 2015. Mike has recently transitioned to academia and is now a full-time researcher in marine geohazards and sedimentology at the National Oceanography Centre in Southampton. Mike's research is primarily in deep water settings, and today he's going to be talking to us about his research discovering turbidity currents in the wild. So without further ado, I'll hand over to you, Mike.
Well, thanks very much, Catherine. Can you hear me okay still?
Yeah.
Yeah, excellent. Okay, so thanks very much for the invitation to give this presentation. So I think one thing I really wanted to stress from these first two slides is this is very much a collaborative endeavor. So I'm presenting some of my research, but really it's nestled in with research that belongs to a whole load of different people. So hopefully in the next 45 minutes or so, I'll share with you what I think are some of the recent exciting steps forward in our understanding of what these avalanches of sand and mud in the deep sea that we call turbidity currents. And this work's only possible through a big international collaboration. So there's a number of institutions and organizations involved here. I show logos. And want to stress that in order to get these sorts of data sets, in order to do this sort of science, it needs big international and collaborative research. So this is very much not my research. This is a whole load of people's research. And in particular, I want to highlight the people in the blue rectangle here. And so these are the PhD students that have really driven forward the research that we've been doing. So throughout the presentation, I'll pepper this with illustrations from their papers that show some of the really exciting changes in our understanding that we've made. And there's a whole range of other people who have gathered field data with us. Going to see needs a whole raft of collaborators, of technicians and of field crews. So I can't name check everybody, but the main people I want to highlight here, and hopefully we'll do so throughout the presentation, is this amazing group of students. And in particular, but this is by no means all collaborators, people who I work particularly closely with from Canada, from the US, and now in New Zealand and in the UK. So without these people, this work wouldn't be possible. I'll try and reference them as we go through, but really do, if you want to know more about this, dig into some of the papers that I highlight as we go through the presentation. So I would guess that most of you have an understanding of what a turbidity current is. It's a kind of a sediment-laden flow that's moving downslope underwater through its excess density, and that excess density is a result of the sediment that it's carrying. They form some of the largest accumulations of sediment on our planet in the shape of submarine fans, such as the Indus fan here. They create some of the longest channels and canyons on the planet, which can rival or even exceed the scale of rivers. So shown here side by side, the Grand Canyon on land and the Monterey Canyon, which we'll come back to later off the western coast of California. And they transport globally important amounts of sediment, organic carbon, nutrients. Now we also think pollutants into the deep sea, but also pose a hazard to important and critical infrastructure that supports our day-to-day lives. Just here is shown a proposed pipeline route across part of the deep sea Indus fan. So avoiding these canyons or channels in this case is not possible in many settings. So we want to understand how they work. How do the flows operate? And actually infrastructure and impacts on infrastructure has told us a lot of what we know about turbidity currents, in particular their velocity and their triggers. So it's just over 90 years now since a magnitude 7 earthquake off the northern coast of America triggered a submarine landslide, which started to mix with the ambient seawater and create a sediment-laden avalanche called a turbidity current that sequentially broke all of the cables that connected North America to the UK. A repeat event, if that occurred today, would be quite significant for the UK and for North America in terms of the bandwidth of the telecommunications that we rely on. Actually, more than 99% of all digital data traffic goes by a global network of telecommunication cables. Most people assume the cloud is in the sky, but it's actually under the sea. And this is not just a one-off. Multiple instances of cables have been broken, particularly where they cross submarine canyons and channels, such as the well-known case of the Galping Canyon off the south coast of Taiwan. And these sequential breaks of cables progressively down a canyon have given us some of the first information about how fast these flows were going. So in both the case of the 1929 Grand Banks event and the Pingtung earthquake in 2006, Typhoon Morakot in 2010, the maximum speeds these flows were traveling was up to about 20 meters per second, and generally decelerating through the system. Well, in this case here, you could see in the lower reaches, actually the flow may have been speeding up. This allows us to tie turbidity currents to things like triggers, earthquakes, tropical cyclones, river floods. It allows us to reconstruct velocity or roughly reconstruct velocity. We don't precisely know which part of the flow actually broke the cable. But it doesn't tell us anything about what the turbidity current looked like, what its internal structure is, what its sediment concentration was. And it's the sediment concentration within the flow that really dictates how it behaves. So we're left with these sorts of schematics, and as geologists and sedimentologists, our job is putting together a picture based on incomplete information. But generally we have paintings and schematics of what we think turbidity currents look like. And we've gathered this information from a range of different sources. And the following slides are by no means meant to demean any of the disciplines involved. It's really just a recognition that each sub-discipline on its own is reporting incomplete information, and we need to get the full picture. So we can make up turbidity currents. So this is some 3D numerical modeling done by a former PhD student, Valenka, looking at fluid supercritical turbidity currents and how they interact with an erodible seafloor. But in order to build realistic models, we need to provide realistic and credible input conditions. If we haven't observed flows actually in the wild doing what they do in nature, then we make some guesses and some assumptions here. So we can look at them at a scaled down approach. And so this is a video provided courtesy of Matthew Cartanian and Joris Eckenhuizen from the Eurotank. We can look at turbidity currents moving down flume tanks, in this case, a pretty large flume tank, several meters long. And we can start to make measurements of sediment concentration and velocity within these flows. The problem is these poor turbidity currents are held captive, and what they really want to do is get bigger and go into the deep sea. So we ask questions of, well, can we scale all of these observations? What aspects can and can't we scale to the deep sea if we know these systems can be hundreds to thousands of kilometers long and flows potentially hundreds or more meters thick? We can map out individual events and look over longer time series at ancient rock records. This is a photo from Steve Hubbard. And we can start to look at the modern seafloor as well and take cores from the shallow subsurface. And increasingly, we're getting higher and higher resolutions of the seafloor as we take little yellow submarines like autonomous underwater vehicles to get multi-beam sonar surveys of the seafloor. And these give us, in some cases, excruciating levels of detail of what the seafloor looks like, but they only tell us what has happened. They tell us how the seascape was molded by a past flow, or what the pathways are, potentially what the frequency of deposits that are in place is. This doesn't tell us anything about the flow itself. So we ideally also want to go into the wild and make some field scale measurements. Now for their onshore cousins, rivers, this is relatively easy to do. It's not easy to measure rivers, but they're far more accessible than the deep sea. And in some cases, you can just wade in. In other cases, you need smarter instrumentation and deployment measures. But we want to see if these beasts, rivers, are similar to the submarine channels that we see on the deep sea. They look quite similar. We have to interrogate them in slightly different ways. And whilst we have millions of measurements of rivers of velocity and sediment concentration, Peter Talling has told many times there's only a handful of places where we have any direct measurements of turbidity currents, and very few to get to sort of estimates of what the sediment concentrations are. So we're left with open questions of how similar or how different these processes and features are. And one of the challenges is because turbidity currents have trashed and damaged and destroyed a lot of the instrumentation that's been placed in their path. It's simply not been possible to get these detailed measurements. And so from a research perspective, that's exciting. It means several fundamental questions remain. It means it's still important to draw together answers from those incomplete or disparate data sets and types. We still have open questions at field scale of what does a turbidity current actually look like? What's its velocity and sediment concentration structure? How do flows evolve through time at one point and downslope? This governs how and where they're transporting sediment, nutrients, pollutants, what sort of fluxes they have. How are they triggered? Do we just need big external events, or can they be triggered in different ways? And how do flows shape the seafloor? How do they build and shape submarine channels? And when we look at the deposits in ancient archives, what are those deposits actually telling us? How faithful are they? And what can we reliably reconstruct from those deposits? There's been an advent recently, I guess in the last decade, particularly the past 5 years, in either using new technology or repurposing existing technology to make the first detailed measurements of turbidity currents in the wild. So the next slide, I'm going to show you some sonar imagery using a 500 kilohertz multi-beam sonar that was originally designed as a fish finder. John Hughes Clarke repurposed this and used this to shine up a submarine channel to image some crescentic bed forms. So here, the top image, we're looking at backscatter. So this is energy that's returned from the sonar. So the white is high backscatter, the black is low backscatter. And so where we have suspended sediments in the water column, they shine as white. So what you're going to see here is a relatively dilute flow coming through, and then further on another flow that's moving about 2.5 meters per second that cannibalizes that flow, and it interacts with these bed forms, these crescentic shaped features within a submarine channel. And for scale here, we're looking at about 50 meters across this yellow bar. We can also look at a non-time synced version of the top image here, a cross section through a bed form, through a very narrow beam looking downwards. And this is like pressing your face on the side of a flume tank, seeing a turbidity current interact with a bed form and speed up and go thin and possibly fluid supercritical over the steep part, and then slow down and expand and deposit on the back of this part of the bed form. So we see these images, and when I saw these images, I've looked at turbidites, the deposits from turbidity currents in cores for years. The muddy and sandy deposits, I treat them as my babies. So it was difficult to work out what I was more excited about, seeing this sonar imagery of a turbidity current, or seeing my baby in an ultrasound for the first time. My wife's not here, but obviously it's the top left one, but it's a pretty close call that I prefer. So one thing I want to stress in this talk is it's really exciting times for turbidity current research. There's a whole raft of different tools that now we can use for measuring not just turbidity currents, but ocean processes and marine geohazards for the first time, to get an understanding of how they're triggered, how they behave, using autonomous tools, using tools that are deployed from vessels. So I'll show just a flavor of some of these different tools and how we use them to make measurements at 4 different sites around the world in 3 different settings. We'll take you to the western coast of Canada, to British Columbia, to the fjords, to Monterey Canyon and Western California, and then offshore West Africa, offshore Angola and the Congo, in the deep water Congo Canyon. We'll look at 3 different systems. First of all, offshore from meltwater fed rivers, which are swollen with sediment discharge during the spring and the summer due to ice melt in British Columbia. John Hughes Clarke, who acquired some of the seminal data here, has described these systems as being geology on steroids. And so here, these amazing systems, in some cases, are kind of mini submarine channels and canyons, So here we have, this is the sea floor that we're looking at. So the red's shallow water, about 0 meters water contour. The blue's up to about 200 meters water depth. So Squamish is a pocket-sized system where we have 3 submarine channels that terminate in these lobes. And in 2011, John Hughes Clarke recorded just over 100 turbidity currents within a period of just 3 months. So a super active site to go and test technology and see how it works in the deep sea. We then go to Butte Inlet, which is a bit further up the coast in British Columbia. It's fed by 2 meltwater rivers, and then it feeds this, this sinuous submarine channel system that feeds down to a terminal lobe in about 600 meters water depth. Then we're going to go to another river-fed system, but this is offshore from the deep water Congo Canyon. And so the Congo Canyon is fed by the Congo River, the second biggest river in terms of water discharge in the world. And the canyon actually enters the estuary. There's no delta to speak of here. We'll look at a mooring placed by Chevron, an oil and gas operator, at 2,000 meters water depth. They're interested in seeing how active this site was because they plan to put a pipeline across the canyon. And then finally, we go to a system which isn't fed by any rivers, and it's actually fed in the present day by the convergence of littoral cells that funnel sediment within the head of the canyon. So the Monterey Canyon, offshore California, offshore from Moss Landing. Santa Cruz is a bit further up here. And we'll look at a remarkable array of more than 50 instruments placed down the upper part of the submarine canyon, down to about 1,900 meters water depth, that track the passage of individual turbidity currents and see how they evolve. So some horrible holiday photos to show you here. First of all, this is the Squamish Delta in British Columbia. So we performed fieldwork here in 2015. John Hughes Clarke has been performing here very regularly since at least 2009. It's a slightly artificial system because a training dike was installed in the mid-1970s here, so the river is pinned in place. You can just about make out here, this is the delta lip, which is exposed at low tides, and offshore from this are the 3 submarine channels, which look like this. What John Hughes Clarke did in 2011 was perform repeated seafloor surveys using multi-beam echo sounders across the entirety of this submarine delta system. And so this is remarkable. For 93 consecutive weekdays, we got an idea of how changeable the seafloor elevation was. And amazingly, it was very changeable. John provided evidence of more than 100 turbidity currents, probably 106 turbidity currents or more, in a period of 3 months in the spring and the summer, due to this meltwater pulsing out from the river. And the next animation is going to be a zoom into this yellow box at the top by the delta lip here. And what you're going to see is each time step on this animation represents 1 weekday consecutively over 3 months. And here you can see a remarkable amount of change. So that the delta lip every so often progrades in response to rapid accumulation from the river. But periodically, bite marks are taken out of this delta lip. Here's another one. So these are between 50 and 150,000 cubic meters in volume. And these are landslides or collapses of the delta lip, which generally occur during low tide. But you'll also see in these 3 submarine channels down here, there are these crescent-shaped features, these bed forms, which march their way back upstream. And these march their way back upstream in response to turbidity currents, which go through a series of erosional and depositional cyclic steps. And they don't all correspond to these landslide events. There's maybe only 5 of these delta lip collapses. So there's another process that's triggering them. But it's a super active site, and it's similar to Butte Inlet, where we've been, where we've measured just over 80 turbidity currents within this system in 2018. Again, it's an absolutely stunning field site to go and look at. But if you look at the seafloor relief, it's as stunning, I think. You see these 2 river systems which feed in here to these pro-deltas, which then coalesce and feed into this sinuous channel system, which goes through a channel lobe transition zone and a lobe here, down to about 600 meters water depth, down through a length of just in excess of 40 kilometers. And so here we placed a number of instruments on moorings to make a measurement of the velocity and the sediment concentration structure of these turbidity currents. And this work involves a lot of people, a lot of field work, a lot of instrumentation, and so very much appreciate everybody's inputs. And this also involves a range of different vessels, from these large Canadian Coast Guard vessels all the way to these smaller inshore vessels. Here's Clare McGee from Newcastle University sampling the delta top sediments, doing provenance and mineralogical analysis as we're looking for source to sink, and also influence of different minerals in coating and binding sediments, which is part of work that I won't be presenting here. This is spawning other research too. The thing I'm going to focus on here is the direct measurements that we've made of flows, and we use these little yellow instruments here called acoustic Doppler current profilers, and these are suspended above the seafloor usually. They shine 4 beams down, and based on the energy that's backscattered within the water column and changes in the Doppler shift intensity, we can understand some proxy for the amount of sediment that's suspended in the water column by these flows, but also create a 3D velocity profile. So here we put these large train wheels or scrap metal down on the seafloor, in this case 1.5 tons weight, to try and stop it moving as a turbidity current interacts with the seafloor. These acoustic release links that allow us to get our instrument back, and we leave the anchors down on the seafloor. And then this large positive buoyancy that houses the instrument to keep it stable. And the turbidity current passes underneath, and so we get a time series measurement of depth versus time, and here we see a turbidity current arrive. It's about 10 meters thick, it's moving up to 2.5 meters per second, and it lasts several minutes. And that's pretty typical for this system, flows between about 1 meter and 3 meters or thereabouts per second. A similar instrument was used, but a lower frequency instrument by Chevron in the Congo Canyon. And so here an instrument, this ADCP, was deployed in a very similar manner, about 85 meters above the seafloor, with a view to understanding what the frequency and type of turbidity currents were occurring within the Congo Canyon at 2 kilometers water depth, a few hundred kilometers offshore. And this really surprised us when we looked at the data. It was Maria Asperos who looked at these data for the first time, following Curtis Cooper from Chevron's initial analysis. And she found within a period of 7 months, the Congo Canyon at 2,000 meters water depth is active 30% of the time. So these turbidity currents aren't several minutes long, they're actually days or weeks long. So 30% of the time, there's a turbidity current going on here. And so Maria showed in her paper in 2017 what the internal structure of these flows looks like. And this challenges some of our textbook views of what we think a turbidity current looks like, and I'll come back to this later. But in essence, we can measure the velocity, look at velocity fluctuations as a proxy for turbulence, and also work pioneered by Steve Simmons at Hull University has allowed us to start to look at inverting the backscatter data to get some idea of the sediment concentrations within these flows. So this is super exciting, and I guess the first order, we see these flows are much bigger than in the delta, in the fjords head systems, up to 100 meters thickness, which is approximately the height of the first terrace. So they're filling the canyon. And their long duration. And here in this system, that the flows are generally days, in some cases more than a week long. So this one longer than a game of test cricket, and far more exciting as far as I'm concerned, but others on the research team disagree with me. And we can start to use these inverted concentrations to make some estimates for how much sediment these individual flows are carrying. So individual flows we think are carrying more than the discharge of the Mississippi River annually, but also individual flows, Maria estimates, may account for, in some cases, 2% of the terrestrial organic carbon that's buried in the ocean. So reinforcing the view that turbidity currents are globally important agents for the transfer of organic carbon. And the next place I'll take you to is California. And so the photo taken here is taken right up by Monterey Bay Aquarium Research Institute's offices. Here's Charlie Paul, who led the research with a large team, and this is just a small group of people involved. But here from Charlie's office or from the beach, you can throw a stone and you'd be able to land it in the head of the canyon. That's how far it cuts back into the continental shelf. And this, I think, is probably the most ambitious attempt to date to measure turbidity currents. all the way from about 200 meters water depth down to 1800 meters water depth. And each location over a period of 18 months, the pathway of turbidity currents were recorded by acoustic Doppler current profilers, velocity sensors. The suspended sediments were caught within sediment traps, and novel instruments like these smart boulders, which record the pressure, the density, and also the inclination and acceleration. So whether these things were rolling at the bottom of a turbidity current or translating, like in a debris flow. And so this allowed us to record what Pete Talling would call a turbidity current racetrack. And so here 15 turbidity currents were recorded within that 18-month window. So a very exciting data set as far as I'm concerned. So I'm hopefully going to share with you in the next few slides what I think we've learned from these data sets. So we can look at the Monterey Canyon data set, and rather than just looking at cable breaks, we can track how the velocities are changing of turbidity currents down the canyon. And we find that in some of the more narrow and straight sections of the channel, these speed up, and these flows are moving at up to 8 meters per second, maybe up to 10 meters per second in the head of the canyon. As the canyon broadens out, progressively the flows seem to start to slow down. Not all the flows made it the whole way through the array. Many of the flows actually stopped within the upper part of the array. And these flows were powerful and capable of transporting instruments with them. And this includes a large instrument which was designed not to move and to remain stable on a tripod frame with train wheels providing almost a ton weight out of water. That instrument that was designed not to move actually was transported almost 5 kilometers down the canyon, entombed within a slurry of sediment that we think moved like a sandy debris flow. It was liquefying the seafloor as it traveled. It also transported one of the moorings that was founded on just over a ton's worth of anchorage. And that moved 8 kilometers, almost 8 kilometers down the canyon. It was damaged. You can see the bending to the steel frame. And here's this heavy instrument that was designed not to move. It had one of these smart boulders attached to it so we could track whether it was rolling. Actually, first of all, it was knocked down to the floor by the flow, and then it was just pushed and translated along the seafloor, stripping paint from it and bending the legs. And this is what it looks like when it was recovered. Just the foot sticking out from the sediment that entombed it. So from these novel measurements, we can start to see what the anatomy of a turbidity current looks like. And so what Maria and Steve Simmons in a paper published a few weeks ago are suggesting is that unlike some classic models based on some flume tank experiments where it's the body that drives a turbidity current, it's the head that then recirculates sediment back, they both find that this frontal cell of high density appears to be where most of the sand is, and high velocity core seems to be driving the flow, and it's moving at speeds of up to or in excess of 2 meters per second. Dan Parsons has likened this to a racing car that's tearing through the desert and kicking up a wake of mud, in this case, behind it, so that the body here and the tail is very dilute indeed. We suspect because of the differential velocities, the head here is maybe moving 2 meters per second and the body at 80 centimeters per second. If we were to keep going further down the canyon and this flow keeps going, basically the head is pulling away from the body and the flow is stretching. Insights from Congo Canyon and also the Monterey Canyon on the right, this is from a paper by Charlie Paul et al., suggests that these flows are capable of transporting and keeping in motion very heavy objects. We think that the basal part of these flows is very, very dense. It's not behaving like a dilute turbidity current from some flume tank experiments. And the dense lower part is also outrunning the rest of the flow and is capable of remolding and potentially liquefying seafloor as it impacts with it. And this is to a depth of a few meters. So we show that flows can be powerful. In places like the Fraser Delta, they've been recorded in excess of 10 meters per second. Tumbling instrument platforms. They can transport heavy objects for several kilometers. We think they're driven by a dense frontal cell. They may remobilize and potentially fluidize or liquefy the seafloor. This is maybe very similar or analogous to snow avalanches, which show this two-phase behavior. Recent work published at the start of this year by Kate Herimer from Durham University shows that the initial velocity of a turbidity current appears to play a very strong control on whether that flow goes big or dies out, whether it is long run out or short run out in duration. So here we show that the distance of run out of turbidity currents down the Monterey Canyon over time. And here you see only a few flows make it a long way. And these are dominantly these ones which were in excess of 5 meters per second, round about when they initiated. Below that, apparently they appear to dissipate and die out quite quickly. There's one other curious flow that occurred between a period where there was much less activity, and we suspect that the accumulation of mud within the canyon and the entrainment of that mud actually changed the flow rheology, but there's still open questions about what controls the run out of turbidity currents. In terms of the duration of flows, we find stark differences between some of the sites that we look at. In the Squamish Delta, we see these short duration flows, which are maybe minutes in duration. In Monterey Canyon and Butte, they tend to be hours, maybe in Monterey sometimes in excess of a day. But in the Congo Canyon, what Maria found was that these flows keep going and going and going and going and going. And we think that these sandy flows, the flows that are dominantly comprised of sand, are these short-lived ones. They show this rapid peak in velocity and an exponential decay. But where you have availability of mud in the system, that this promotes long-duration flows, which in some cases can maintain suspension of mud at, let's say, tens of centimeters per second, and that promotes their long duration. And so work soon to be submitted by Daniela Vendatoli is demonstrating there are these two end members of either mud-rich, which are very long duration, which show this steady plateau. This is normalized to flow velocity and duration, this plot, or else a rapid increase and an exponential decay. But you don't get one or the other. You actually get a gradation of behavior between these depending on the amount of mud and sand that are available within the system. So Kate has shown that initial velocity threshold appears to control the run-out distance of flows, but that the substrate may also play a role. And Daniela shows that the grain size that's available in the system appears to be the dominant explainer on their structure and duration, and this is independent of the type of trigger or the type of system. I've been particularly interested in how turbidity currents are triggered, one from a hazards perspective, if we can start to predict these flows, but until we've had large n-number data sets, it's not been possible to do that. PhD student Lewis Bailey at Southampton University is now looking at multivariate statistical approaches to try and predict turbidity currents based on different environmental variables, and is making some good success there. But the other thing we want to do is see whether we can reconstruct, say, terrestrial hazards such as river floods or earthquakes or tropical cyclones from the deposits that are left behind. But for us to be able to reliably do that, we need to be able to reliably link those events, or the turbidity currents, to initiating events. And undoubtedly in some systems that may be possible, and lakes for sure, in some cases that seems to be very reliable. However, in systems particularly offshore from rivers, and here based on the Squamish Delta, we see multiple competing or compounding processes that can trigger turbidity currents. So there can be a lot of non-uniqueness. And that's exactly what Lewis Bailey found for the Monterey Canyon, which is not directly fed by rivers. Here he found that none of the 15, there was no common trigger for the 15 different turbidity currents that were recorded. He also found, in the same as we found for the Squamish Delta and Congo Canyon, that none of the turbidity currents actually relate to large external triggers like earthquakes or large floods. What Lewis actually found is that a combination of different variables can trigger turbidity currents, but they're actually best explained by the cumulative sediment buildup in the head of the canyon, and that preconditioning may be much more important than instantaneous triggering. He looked at wave energy, storms, tidal elevation, river discharge into the bay, internal tidal velocity, wave direction, and earthquakes, and found that some events here actually have no high wave energy, no high river discharge. There's apparently nothing going on this very quiet Wednesday. Yet this is one of the most powerful turbidity currents. But it does occur after the highest cumulative buildup of sediment in the head of the canyon. And he's compared these results from Monterey Canyon with measurements from Squamish, from Butte, from Congo Canyon, so from 3 very different systems that are fed in different ways, and in some cases by rivers with very different discharges, and has found that they all show some seasonal clustering of switch on, and that largely, well, almost exclusively, the switch on for these systems occurs when the sediment supply is highest. And so this is pretty intuitive, but we see it with data for the first time. And that turbidity currents either occur after rapid sediment supply, or in some cases, such as in Monterey Canyon, they occur after a large cumulative or total sediment buildup. And this may be to do with the progressive buildup of excess pore pressures in the subsurface, and then slumping and failure of those materials. So the key take home from Lewis's work is that preconditioning appears to be much more important than the trigger, and multiple different small processes can actually lead to turbidity currents, but the sediment supply is the key thing. We can also start to use some of the direct measurements to mechanistically look at how different processes operate. So the next image here is time-lapse multi-beam profiles of the water column acquired by John Hughes Clark from Butte Inlet, going backwards and forwards every 15 minutes at different stages in the tidal cycle. So here high, and here low tide. And here, the white here provides evidence of increased backscatter, and so this is largely sediment. So we can image the pycnocline, the freshwater saltwater interface. We can see sediment that's pretty much always raining out from this homopycnal, this surface plume of sediment. But only every so often do we see a turbidity current like here, moving at several meters per second down the canyon. And these are dominantly occurring coincident or approaching lowest tides. And so Sophie Hage took some of these observations. She also looked at ADCP backscatter data and inverted that to get some idea of the sediment concentrations, and found that sediment concentrations are highest during low tides. So either sediment is flushed off the top of the delta and or it's concentrated as a turbidity maximum up at around this location. And as that sediment reaches a critical threshold, it is every so often capable of creating a turbidity current which ignites and runs off down the slope. And so Sophie showed that for this system, which is offshore from a pretty dilute river plume, you can initiate turbidity currents under lower sediment concentrations than we previously thought possible. Previous seminal work by Mulder and Svitsky in '95 suggested that turbidity currents by hyperpycnal turbidity currents, so those which plunge due to their excess density within seawater, were only possible within 9 of these kind of dirty river systems. This was advanced by laboratory experiments by Parsons et al., who documented another mechanism for kind of quasi-hyperpycnal settling through these cascading density fingers that can meet the seafloor, and suggested an order of magnitude greater number of river systems may be capable of triggering turbidity currents in such a manner. Sophie's work actually suggests her density threshold, which is much, much lower, but maybe 146 rivers worldwide are capable of initiating turbidity currents. Obviously, there are more factors than just the density contrast that are at play here. And there may be other competing factors, such as strong along slope currents, which may disperse sediments. But this may point to one of the reasons why we see flows at a higher frequency than we ever imagined we would do at some of these systems. So Lewis has shown that major external triggers don't necessarily, they're not necessarily needed for flow initiation. Obviously, earthquakes and tropical cyclones in some systems can trigger flows, but you don't need them. Sophie's work along with that may actually explain that relatively small combinations of variables and preconditioning might explain why flows are far more frequent than we anticipated in the systems we've looked at. And Sophie's work also shows that there's a very effective link at low tide between rivers and the deep sea. And this has led on to work that Sophie has developed with Valier Galli and others at Woods Hole Oceanographic Institute, which is published a couple of weeks ago in Geology, where she shows that these flows are also very efficient conveyors and transporters of not just organic carbon, so dominantly petrogenic, kind of old organic carbon within the kind of the Bauma TA part of the sequence, but even within the upper sandy parts of deposits, we see high concentrations of woody and leafy debris, this young biospheric terrestrial carbon, which is then capped by muds, which potentially keep that carbon buried and locked in. And unlike some river systems, the organic carbon, this modern fresh organic carbon, shows an affinity with the sand and not with the mud. So some interesting results here, suggesting that on an individual flow basis, within these river-fed fjord systems, the organic carbon burial is very important, and that we may have missed out an important part of the global carbon budget when we look at submarine channel systems. Sadly, because turbidity currents are capable of transporting nutrients, organic carbon and sediment, they can also carry other anthropogenic particles too. And Martina Pierdomenico showed in the paper in Scientific Reports last year quite how polluted some submarine canyons can be, and also what the efficiency of transfer is in ephemeral flashy systems. So these are canyons linked to onshore fiumare systems. And so here she showed huge amounts of macro litter, including this creepy baby doll whose eyes are missing when the ROV flies over it. And this extends to several hundred meters water depth. You wouldn't imagine you were looking at a submarine canyon. You'd imagine you're looking at a garbage tip. And Florian Pohl has started to extend that work by showing how these submarine canyons and turbidity currents within them can be highly efficient, at least at an experimental scale, in transporting and preferentially sequestering microfibers, so microplastics. And there's lots more work to be done in this field, perhaps linking this with organic carbon as they have some very similar hydrodynamic equivalents, at least between some types. So we've shown that flows can sequester important amounts of fresh organic carbon as well as pollutants. Open questions now are about the efficiency of that burial and about what timescales it's efficient on. So this is really exciting work published by Daniela Vendatoli last year, looking back at the Squamish Delta. And here we're looking at a profile which goes from the northeast down to the southwest in the upper part of the central channel. And Daniela showed over each one of these time steps, which is a weekday, how the stratigraphy is built and how even over a few days, because of the upstream migration of these bed forms, you can rapidly rework sediments which were deposited. Sophie Hage then started linking those deposits, at least these synthetic deposits from time-lapse bathymetry with sediment cores, and showed that indeed, yeah, we only see a small part of these deposits which are preserved. Whilst on the face of it, we'd think we'd see these low-angle backsets in cores, what we actually see are massive sands, and over time, all that's left and recorded under this aggradational regime are these lenticular bodies of massive sands. And these are what we see in other places in some proximal submarine channel systems. So the preservation, as shown by Sophie and Daniela, even over just 3 months in a proximal system, can be very poor. So here's a long strike section going through here, this northern channel. What you're going to see fairly soon is one of these big delta lip collapses that then plugs and fills the channel, smooths it off. But that's rapidly reworked. It's then incised, the channel will then fill in with another delta lip failure, and then it will become incised again. So the stratigraphic completeness and the story is very complicated here indeed. And Daniela shows that over the whole delta, over just 3 months, the stratigraphic completeness is about 11% on average, the mean. And indeed, in some locations, channel lobe transition here, there's nothing left of the deposits because of incision. And so the last piece of the story I'll talk to you about now is extending this time scale. The vision is to integrate this with deep time records. We recognize there's limitations of what we can and can't do here. We're starting to get data sets now that show us evidence of 10 years worth of change. This is really exciting work that will be published, I think this week, by Martin Heinen, PhD student at NOC in Southampton, that looks at full source to sink differences over a submarine channel system. So here we see elevation changes of up to 30 meters, and we see down from the lobe deposition, but also these cyclic changes in erosion, deposition, erosion, deposition, erosion. And Martin's looked at a series of these repeated seafloor surveys to document how the seafloor is changing. And yes, we see a bit of outer bend erosion. Yes, we see evidence of upstream migration of crescentic bed forms. But what dominates the erosion and the deposition are like waterfalls under the sea. These nick points, which are close to angle of repose, steep steps that are up to 10 to 30 meters high, that migrate hundreds of meters or a kilometer per year, and they create these zones of erosion and deposition. And so Martin's created these beautiful animations that show within the submarine channel, the flow would come down this direction, these steep steps, and here we have a profile going through it, and as the nick point retrogresses upstream, we see in some cases 20 meters or more of erosion, which more or less we think occurs instantaneously based on direct measurements. And this occurs instantaneously as a powerful and dense turbidity current flows over them. So in this particular system and other systems, we think, certainly here in Butte, more than 75% of the erosion is attributable to these nick points and not the growth of meander bends. So some systems certainly behave very differently to rivers, and this builds on some work that Jeff Pekel and Esther Sumner have published previously. And now Zaki Zulkifli at Southampton, who started his PhD in September this year, is looking at a longer time-lapse bathymetry data set from night inlets, so quite close to Butte. We have this beautiful river-fed system here going down to a terminal lobe, this lovely system, and we see a whole range of different changes. Crescentic bed forms and landslides up on the pro-delta, nick point retrogression within the channel axis. In some cases, some more conventional kind of sweep and swing type erosion in meander bends, but also these bends where cutoff doesn't appear to be occurring, and instead nick points are migrating the whole way around the bend here, several hundred meters, or in this case, in excess of a kilometer over a 13-year time series. So multiple different processes operating on different timescales, and that will affect our interpretation of the rock record. So we show over the timescales that we look at, we already knew this, but the stratigraphy can be highly incomplete, and that's because flows fundamentally shape the seascape. And submarine channels that we've looked at appear to be evolving largely quite differently to rivers. So I'll leave you with the following conclusions. The first is, yes, we can. It is possible to monitor turbidity currents. We have suffered misadventures. I've circulated this paper with the talk advert for some examples of where we've had gear and equipment that's been trashed by flows and some of the lessons we've learned. So it can be risky, but it's certainly possible. And I think the big step changes in turbidity current research have largely come from step changes in technology or different methods of data acquisition. So we are still continuing to learn by seminal work such as Coonan and Migliore in the 1950s. We can start to test some of those theories and other theories based on deposits and flume tanks at field scale. We can start to consider what we can and can't scale from lab experiments. There's a growing need to integrate with the depositional record and understand the frequency and magnitude scale of these events. And I want to leave you with the fact that deep sea sedimentology really matters. I'm talking to you in some cases from the other side of the world through a high bandwidth internet connection. And that's only made possible by this global network of telecommunication cables. They're about the diameter of a hose pipe. These are hard questions on this slide to ask yourself. Could you go 11 days without the internet? Particularly developing economies which have very few cable connections often find this out the hard way. So it's really important to understand the hazards that face this global network of seafloor telecoms cables to ensure that, well, developing countries, and particularly small island developing states, can achieve the sustainable developing goals, but also particularly in the lockdown, that we remain connected to each other, and we can do things like Seds Online. So I think I've exceeded my time, so I will stop there, Catherine.
Thank you so much for that, Mike. It was fascinating. It's amazing to see all these systems that we can't otherwise see, and all the data that's
Sorry,
invisible.
just cut out, Catherine.
Okay. So we're just asking the chat now for questions. So if you have any questions for Mike, please type them into the chat, and then we'll go through them one at a time. And if you're watching this on a recording, there is a thread on the forums for Mike's talk, so please go and ask your questions there. And the same applies to you guys if you think of a question later on that you'd like to ask. So we'll start going through the questions now then. Okay. Lots of people think it was a great talk then, Mike. Lots of thank yous.
Well, thanks very much.
We have a question from Jim Best saying, great talk, Mike. On preconditioning, is there any evidence that breaching and headcut erosion of accumulated sediments at the top of the canyon plays a role in generating density currents?
Great question, Jim. Yes, largely indirect. We certainly see evidence of things that we think look like breaches and headcut erosions. In the Squamish Delta, the time-lapse bathymetry surveys that we have are pretty much daily. So we see evidence of kind of lateral unloading or headcut erosion there, but the sediment supply is so large that it basically fills the system back in again. I think if I share my slides now, if you can still see them, certainly places like the seafloor of the Monterey Canyon, there's a video here showing retrieval of some of these beds, these benthic event detectors from the seafloor. You'll get some idea sped up what the seafloor substrate looks like, but how mobile it is and how easily disturbable it would be. And certainly I can envisage processes like Dick Masbergen's shown in other systems that the breaching would be likely here. Del Taras have been doing some exciting experiments in the Westerschelde estuary, actually trying to trigger submarine breaches. We were involved with one of those experiments. So I don't think we have a lot of evidence. I'd like to do more repeat surveys at the heads of canyons and deploy more instruments towards the top. The challenge is more instruments closer to the top of the system are more vulnerable to the very powerful flows, so might not last so long. I suspect it's very important. We don't really have a good feel on how they initiate, other than they start at the top of the system in places like Monterey Canyon.
Thank you. Next question is from Claire McGee saying, great talk, Mike. Just wondering if there are any observed morphological differences between muddy versus sandy canyons, less, more meandering, knife point migration, question mark.
Yeah, and good question, Claire. In general, we kind of have a gut feel that there probably are. This is work that Martin Heinen and Martin Hassenhundel from Technical University Vienna are looking into from the Congo Canyon system. It's a big project led by Peter Talling, involving a lot of people. We haven't often got the resolution of the multi-beam data, often because it's shipboard multi-beam data, so we don't quite get bed form resolution. Daniela Vendatoli looked into this in her EPSL paper last year and kind of posited that we'd expect muddy systems to have fewer crescentic bed forms, and that we might expect to see more meandering of, more migration of meanders. We certainly do see evidence in some muddy systems for nick point migration, but this is a question that's really open for more data gathering. More high resolution surveys and time-lapse surveys will provide answers there. We have been biased largely to sandy systems that we've looked at because we've been looking at very active systems. So it would be very interesting to look at other systems, let's say, for example, the Amazon, the Indus, to really examine what the differences are. So if anybody is interested in deploying instruments, is working in those systems, we'd certainly be happy to hear from people.
Great. Next question's from Ant Morgan, saying, really interesting talk, thank you for sharing. How do the long-lived turbidity currents of Congo Canyon differ from conturites?
And this is the turbidity currents rather than the deposits themselves. So, I mean, I guess they're quite different because these are likely to be higher sediment concentration, even though they're relatively dilute for turbidity currents. The shape of the velocity profile is going to look quite different as well. And the way in which they're driven is different. There's a good question here more generally, and this comes has come as quite a big surprise to me, is there's been quite a lot of work in the oceanographic community on thermohaline-driven circulation to understand global changes in temperature, carbon flux, salinity, all those sorts of things. And the instrumental arrays that are placed across places like the Atlantic, things like the Ellet line, these are very low frequency instruments, usually 75 kilohertz frequency acoustic Doppler current profilers, and they don't record information near the seafloor. They certainly don't capture that benthic boundary layer and that interface, and they're not resolute enough for us to start to look at small scale turbulence or to look at suspended sediment concentrations. So it surprises me because contour currents themselves should be much easier to measure because they're generally slower than turbidity currents because they have lower sediment concentrations. So there's definitely an open goal there to deploy arrays of ADCPs and other sensors and sediment traps to really better understand the sediment dynamics of contour currents. So some fundamental differences, but actually the data aren't really there. There's people like Elder Miramontes who are doing pioneering work off East Africa, for example, to try and characterize those sorts of flows, but not a huge amount of data that actually talks to us as sedimentologists, mostly to physical oceanographers.
Great, thank you. Next question's from Drew Phillips, saying fantastic and ambitious observations. Could the very long flows, such as in Congo Canyon, actually be amalgamations of many small flows rather than single events?
Yes, I mean, we've certainly discussed that amongst ourselves, and one thing that Maria Asperos pointed to in her paper, and Steve Simmons also talks about in his more recent paper, that this frontal cell appears to be moving very fast and the body's moving relatively slowly. And Pete Tallings kind of always mentioned, if you roll a marble at 2 meters per second and one at 0.5 meter per second at the top of the canyon, by the time you get to 200 kilometers offshore, they're quite far apart. And so we could envisage that if flows keep stretching, they'll last longer within the canyon, and therefore you might get this traffic jam of turbidity currents further down the system. So it's entirely plausible, and it's interesting seeing, looking at multiple moorings. Something that we hope to do on future projects in the Congo Canyon is to see, do we see the evidence of faster turbidity currents intruding into the back of other turbidity currents? We can start to test some of the flume-based work that Rob Dorrell and his students have been doing. So we don't really know, and we need more data to test it. That's probably going to be my answer to every single question. Is good question. We need more data. Let's go and get some more.
That's what science is for. That's absolutely fine. Our next question is from Aaron Lim, saying, great presentation. All the work you mentioned describes using inverted sediment concentration derived from ADCP backscatter, CP backscatter. Is the ADCP backscatter not useful for this kind of work? Is there a resource online on how to convert ADCP backscatter into inverted sediment concentration?
Well, there is now. So Steve Simmons' paper that's published in Journal of Geophysical Research a couple of weeks ago provides a detailed approach to the method that Steve has developed and built on earlier models such as Thorne and Haynes, which take acoustic backscatter from ADCPs to try and get to estimates of sediment concentration. There's all sorts of uncertainties there because the backscatter is often affected as much by the sediment concentration as it is by the grain size that's in the flow. So there are uncertainties there, and so Steve lays out a methodology for using multiple different frequencies to try and arrive at the best solution for the inversion of that backscatter. We certainly use the velocity data from ADCPs a lot. one of the challenges we also have with ADCPs, or at least a lot of off-the-shelf ADCPs, are that we're looking at 4 beams that shine down towards the sea floor, but they shine down to the sea floor at an angle of about 20 degrees from the vertical. And so what that means is the different beams are intersecting different places within a flow. And so if it's very variable, we can derive quite different velocities. And so sometimes the data gets rejected because of too much error between those data. The other thing is the backscatter is being measured at different parts within the flow. And so if the concentration varies at different places in the flow, there's a challenge. And the other problem we have, or 2 other problems we have, are that because the beams are inclined, we get side lobe interference, which means we don't always get quite close to the sea floor. And in very high sediment concentrations, we actually can't image within the flow at all. So there is a need for more instruments to calibrate that backscatter inversion. People like Sean Ruffell at Newcastle University with Jeff Neesham and others are developing conductivity sensors to make in situ measurements of concentrations within high concentration flows. So these are really kind of first steps and our first views into turbidity currents from ADCPs, but what we really need are multiple frequencies, ideally with beams that are looking down to seafloor and with calibration at different elevations within the flow.
Great. Our next comment is from Tim Demko, who has decided he's graded your room at 9 out of 10, saying no books or maps, but many guitars. So
there's a book I have. Yeah, thanks. I'll take 9 out of 10.
Great. Great talk, Mike. From Francis Lee Bryan at Calamba. Great talk, Mike. With regards to turbidity currents caused by sediment loads, is there a mitigation method that can be applied?
So I wonder with this question whether it's about mitigating the turbidity current from occurring in the first place, or whether it's about mitigating the effects of a turbidity current, say on seafloor infrastructure. Historically, there have been efforts to let off dynamite to try and fail slopes so they don't happen again. They've largely been unsuccessful. We were involved in a dredging experiment with Deltares to try and trigger a breaching failure in turbidity current. We struggled to do that successfully. I think actually if you're looking to mitigate, the best thing is to try and understand the sediment supply to the system, the dynamics of the system, and how likely you think flows are going to be and what sort of flows to expect. We're trying to, within our kind of broad international collaboration, to try and typify different types of systems and settings so we can give some generic guidance. In terms of mitigation of the impacts on pipelines, for example, the ideal thing to do is avoid. In some systems like the Indus fan, maybe you can't avoid. So different measures such as rock dumping, but that may change the roughness of the seafloor, change the diameter or the cross-sectional profile of the pipe. So for example, a vortex shedding stake type profile that looks like the wing of an aeroplane. They're possible mitigation measures, but in some cases where there's a dense flow and say the pipeline's empty, that pipe can behave like an aeroplane wing and just lift off the seafloor. So there's certainly scope for engineering-based studies that test different mitigation measures. And I know that Gwyn Linton and others at Natural Resources Canada and the Canadian Geologic Survey are really interested in testing different types of mitigation in situ to see how do pipelines, cables respond to different impacts or different types of turbidity currents. For cables in the deep sea, largely they're unarmored, but they're relatively small diameter, so there's a small cross-sectional area that's exposed. But if you get a flow that's 20 meters per second, chances are it's going to break everything in its path.
Yeah, it's a challenge.
Thank you. I mean, it's an interesting challenge, and it's an interesting one because it's a cross-section of where sedimentology, oceanography, and engineering really have kind of a crossover.
Absolutely. Our next question is from Valentin Zucat. He says, great talk, Mike, and great guitars. Quick question, do you see any effect of daily discharge variation in these high latitude systems on the triggering of the turbidity current? And do these changes in discharge match the tidal cycles?
Try and get my head around the question. Do you see any effect of daily discharge variation in these high latitude systems on the triggering of the turbidity current? Right. So this really kind of leads into Lewis Bailey's ongoing work on multivariate statistical analysis. So what we found previously, I found, John Hughes Clark, Sophie Harsh have found for places like Squamish and Butte, that you only get turbidity currents when the river discharges above a certain threshold level, and that's about 250, 300 cubic meters per second in those specific systems. That probably doesn't hold everywhere else. Sophie shows that you pretty much only get the turbidity currents coincident with the low tides, and she attributes that towards a concentration of the turbidity maximum towards the head of the channel, the canyon. So yes, it's a combination of, you need the sediment supply. There's also some hysteresis through the system. So the suspended sediment or the bed load transport within the river is variable through time, seasonally, as well as in response to different discharge pulses. And the discharge from the delta top, though, is usually almost in phase with the tidal changes. So yes, we do. It can be complicated in some cases where we think that we get cumulative buildup of sediment and buildup of excess pore pressures in the subsurface, and then tides just tip it over the edge. We can get some lag of the triggering of flows. But in those sorts of systems, there seems to be quite a good link between river discharge and tidal cycles.
Good. That's great. It's nice when things line up. Our next question's from Dan Tech, who says, amazing stuff. Thanks, Mike. Do you think all turbidity currents are driven by a dense basal layer, like those that transverse levees, for example?
No. And I think that people have shown evidence of that. I think even in places such as Esther Sumner's work in the Mendocino Canyon, where she took a remotely operated vehicle and flew it into an active turbidity current, that was a low density flow, but there's still a relatively high concentration layer within the base. I think less than 0.04% concentration by volume, and a much more dilute upper part. Ed Pope at Durham University is working on some really interesting stuff that talks about how flows evolve, and flows that maybe start as being driven by a dense basal layer no longer maintain that dense basal layer as they start to dissipate, and that might be what you see on the levees. I'm not convinced that we've seen anything that hasn't done that, but we haven't looked at systems that might be more typified by dilute muddy flows. So again, it's an interesting open question, and something that Daniela Vendatoli has been looking at when she has these two end members of kind of muddy versus sandy flows. At least in all the flows she's looked at, there is always some initial kind of higher concentration pulse of higher concentration material.
Great. Sarah Giles has our next question. She says, great talk. Have you observed patterns in the lateral scale of facies transitions for deposits of turbidity currents, i.e. at what scale do deposits transition from sand to silt? Me
personally, no. Lots of people have, and lots of people who are dialed into the chat here, so I won't provide a decent answer for this. It's an interesting one as to what lateral scale the deposits transition from sand to silt, and this is variable between the different systems that we've looked at. Will Simons published some really nice work a few years ago in geology on the Monterey Canyon, linking sediment traps, the acoustic Doppler current profiler data, and then the deposits looking at different transects. So I'd point you towards that. Certainly in Monterey, it's the axis of the channel, which is dominantly massive sands and gravels. And outside of that kind of axial filament, which is about 100 to 200 meters wide, then you start to get into the siltier and muddier deposits. But it's variable on a system by system basis. And I don't want to provide an answer when I know that lots of people will judge me on providing a terrible one.
Okay, to be continued another time. Maybe that's a question for the forums then, that everybody can get in on.
Yeah, I think lots of people can dip into that, and people like Sophie Harsh Kate Harrimer are really doing some detailed work looking at the sediment cores from the systems in Butte and Squamish. So, and Meg Baker, now at Durham University, formerly of Bangor, is working on the Congo Canyon system. So they will no doubt have really good observations to contribute.
Fab. Next question then is from Tim Cullen, saying, "Hi Mike, brilliant talk and lovely guitars. Really enjoyed it, especially the discussion on dense basal layers and fast heads you're seeing in flows. What range of grain sizes were you seeing within these flows, if that could be determined? And do you think that having broad or very coarse grain size ranges could form a possible mechanism to trigger the separation and settling up of very dense basal layers?"
Yeah, this is another good question. So the range of grain sizes we've seen kind of range all the way through kind of cobbles and gravel and coarse sand in Monterey Canyon to kind of coarse, fine sand, silt in Squamish and Butte, and dominantly mud. And the deposits at 2,000 meters water depth that have been recovered in the thalweg of the Congo Canyon are really dominantly clay with silty or fine sand bases and quite a lot of organics. That being said, that's what gets deposited, and we think in the Congo Canyon, what's deposited is largely what happens from that kind of collapsing tail at the end of the flow. And the rest of the flow, based on the estimated shear stresses that Maria Asperos and Matthew Cartigny have calculated, suggests that the sand and the silt is probably all being transported further down system, and that certainly tallies with work that Natalie Babineau and others from Ifremer have shown, where there's kind of a tank of sand further down the system. So I think the second part of the question about the range of grain sizes and also the distribution of grain sizes, I'm sure that plays a role. We haven't looked into that. There's some great data sets, such as Katie Meyer's work in the Monterey Canyon, her paper in Frontiers in Earth Science, maybe a year or two ago, that compared sediment traps with the seafloor sediments. So what's suspended at one height within what's actually deposited on the seafloor. They give some insights. I definitely think that the distribution of sediment could make a fundamental difference to the structure of the flow, but we haven't had that control, and it's something that's exciting to explore. I think Daniela Vendertueli's work provides a good step forward to linking grain size to flow structure and behavior. And again, I'll cop out, there's loads more to do. We'll be busy.
That's good. Okay, good. So our last question then is from Jakubas, who says, "Fantastic as always. What technological advances are needed to measure velocity and concentration close to or at the sediment-water interface?"
Good question, Yako. You leave it on the tricky one. This is kind of the holy grail for us, because we care about the sediment concentration of the flows. We particularly care about the highest concentration of the flow. We particularly care about the interaction and the interface with the seafloor and what that exchange looks like. We want to build more robust erosion laws, and we struggle to do so at the moment. Acoustic systems like ADCPs, the frequency range that we're looking at, don't allow us to get right down into the flow. Other instruments, Steve Simmons has worked on development of high frequency instruments that can be placed near the seafloor, and provided they can be designed to withstand that interface, then they provide some really valuable information. There's lessons to be learned from the snow avalanche community, who've buried things like ground probing radars beneath the snow pack. That's obviously challenging in deep water, but maybe there's opportunities to do that. And they can actually record how the interface and how the erosion evolves through time, and get some estimate of the concentrations near the seafloor, in that case, near the air-snow interface. Other experimental work that's been done has looked at similar tools like ground probing radars. Jamie Hissett should have, in his PhD thesis, looked at electrical resistivity tomography, an inversion of that to image the interface. And Sophie Hage with Mark Vardy at University of Southampton have also deployed high frequency chirp systems that have a sweep which is just higher frequency than you'd be using to image the subsurface. that have shown some promising steps forward at imaging at sub 5 centimeter resolution, where we think we can image the seafloor, we think we can image dense near-bed basal layers, but there are big uncertainties in transforming the attenuation and the frequency and phase content of that chirp data into sediment concentrations. I mean, Jaco's really kind of got to the heart of what I think is holding us back at the moment. There's certainly scope for transfer between disciplines and taking instrumentation that has been developed and deployed in the estuarine community and taking that, and also in high concentration rivers, and deploying that in the deep sea. It all needs pressure housing. It all needs power connection. Other things that I think will be transformative is work that Pete Talling and others that are driving using hydrophones and ocean bottom seismometers to listen for to passively detect turbidity currents, so to listen to them. An initial work that's been done by Gwyn Linton, the Canadian Geologic Survey, and by Steve Simmons, is suggesting that we can hear turbidity currents, and not only can we hear them, but we can hear different parts of those regimes. We can hear dense, kind of collisional grain regimes, as well as dilute turbulent regimes. We need calibration of that. But I think there's some really exciting steps forward to come in that area as well. What we need are really resilient instruments that can stand up to being placed in the pathway of flows that can reach 10 meters per second, that can measure high sediment concentrations, that can provide data in real time. So there's a huge amount of technological challenges, but these are areas that a number of different people are tapping away at. And this crosses estuarine, deep sea, oceanographic research, as well as the sedimentology that we know and love.
I think that's a perfect place to finish, because we're talking about all of these spaces to watch in the future, and where the science is going. So I think we'll finish by saying thank you again to Mike for giving an excellent talk, and then giving some amazing answers to some questions as well. And we also hope to see you all. Are we getting some rounds of applause? So thank you. We hope to see you all next week for our third instructional webinar, which is going to be presented by Pierre Pofal at Queen's University, Canada. And also remember that we have coffee breaks 5 times a week in various time zones and locations, so you can all attend one if you'd like. So please come along to them and see our website for details of times and locations. Also, last but not least, if you can't get enough of our webinars, do check out the meeting library, and you can check out some of the things that we have, some of our speakers who we've heard from in the past as well, which is amazing.
Yeah, I guess if I could just add, I mean, thanks to Seds Online for the invitation. Also for the announcement for those that haven't seen it, that the British Sedimentological Research Group will be holding its annual general meeting, so our yearly conference, online through the Seds Online portal. So this provides a really exciting opportunity for this to be our most inclusive and wide-reaching conference that we've ever had before. So encourage people to look at the link, encourage people to join in. And yeah, thanks to Seds Online for hosting this.
Not a problem, we're really excited for it. So yeah, see you all at BSIG as well. We've got 6 months of prep ahead of us. With that, I think we'll say thank you and tie off, and see you all next week, if not before, at a coffee break. So thank you all for coming.
Thanks very much.
Thanks, Mike.